Okay, so we're gonna do 2.4 continuity. Oops. Continuity. So function is continuous, there is no holes, no break, no asymptote, right? Okay, so we said that we draw the curve. Oh, let me hold on 1 second. I need a spotlight my camera. Wow, almost. Can I use today's YouTube video too? Okay. So we draw the curve without lifting pencil. Okay, that is continuous. Okay, then we should do a little bit advanced, right? All right. What do you think about this one? So we have like that, okay? This is not, let's say that this is f of x. The function f of x is not continuous. So continuous. Yeah. Let's set a here. Okay. Because f of a is undefined. Okay. Can you see that there is a hole? So we set that undefined. So this kind of form, which is like what we did the last time, if we have the function x squared minus 4, x minus 2, then this will be x minus 2, x plus 2 over x minus 2. Then we simplify. Oh, we should make it positive. How about that? No, negative. That's fine. Negative. That is correct. That is correct. Negative 2. That is correct. So this is x plus 2, right? Okay. Then the straight line, the domain in this case cannot be equal to 2, right? Because denominator, when x equal to 2 is undefined, right? So we conclude this kind of function is not continuous at a, because f of a undefined. So f of 2 is undefined in this case, right? Okay. How about this? Type 1 and type 2. How about this? This is f of x. So this kind of a form also not continuous. So let me write down continuous like this, CTS with a capital letter, okay, at A, because the limit does not exist, right? Okay, we did this one-sided limit for the piecewise function. So look, we have x approach to A from the left. What do you get? From the left, 1. Okay, good. And if we have x approach to A from the right, what do you get?
2.
T. So, does not agree, right? So we say that does not exist for the limit, all right? Let me write down type 3. Let me erase this one. Type 3. So look, this one. Okay, and here. This one, say f of x again. So function f of x is not continuous at A because limit when x approach to A, f of x how about this one? How about this one too? So what is this? When x approach to A, what is the function? The limit of function. Function.
1.
It's 1, okay? How about f of A?
2.
2. Good. Excellent. So this is not same as, right? So we say that the function is not continuous at A, at the point A, okay? So overall, we have 3 types of the discontinuity. Okay, let me write down about the continuous. Definition, continuous. A function f of x is continuous at a point A. So let me denote IFF means if only if, okay? Means that in the math, we say that this way make a true statement, also this way also make a true statement, true statement, okay? So if blah, 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 then that is true, blah, blah, blah. It's hard to say. Anyway, let me write down here first, okay? Let me explain.
Sorry, what's IFF?
That's correct. If only if.
Oh, okay.
Let me explain the this way, other way, okay? All right, so first one, f of a is defined. Okay, and second one, limit exists. Third one, limit exists. We say that, right? Then the limit is the same as f of a, all right? Okay, so if only if means if the function is continuous at point A, then three conditions are satisfied. That is a true statement this way, okay? I'm going to this way. If the f of a is defined and second condition, limit exists, and third condition, limit exists, the limit is the same as f of a, then we say that the function is continuous at a point A, okay? So this way true, that way true, vice versa. So we called if only if, okay? All right, so it must satisfy the three conditions at the same time, all right? Then we can say that the function is continuous, okay? Let us do this one. So example number one, we just did earlier. That is x squared minus 4 over x minus 2. So let us do this one. Determine whether the function f of x equal to negative x squared plus 4 if x is less than or equal to 3 and 4x minus 8 if x is no space, x is greater than 3. It's continuous. Let me denote to continuous like that. At x equal to 3, justify the conclusion. Okay. All right. So first condition, we have to make at x equal to 3 defined, right? So if the first one, check f of 3, which one we have to use it?
We'd have to use negative x squared plus 4.
Good. So negative x squared, so 3 squared plus 4. So what do you get?
13.
13?
Yeah, 13.
Negative 5.
Negative 5. I told you, I don't trust you. Negative 5. Okay, so second one, we need to check the limit exists. Okay, so I'm just kidding. Oops, it's a 3. Okay, so it's better we draw the graph, right? So this will be more like that. And this will be 3. And then here, like this. Okay. Oh, this is open because the straight line. All right. So we have to check left or and right, right? So let's check the left first. So when x approaches to 3 from the left, what do you get? Hold on 1 second. Let me see. Hold on. You need a label here, right?
Yeah, it'd be -5, right? Coming from the left.
And x approaches to 3 from the right. What do you get?
Is that 4?
It's a 4, okay? They don't agree, right? So we don't say that limit exists, okay? So limit does not exist, right? DNA, right? We know that does not exist, okay? So since second condition does not satisfy, we don't have to check the third one, okay? So we can say that not continuous at x equal to 3. Okay. Anyways. For determine whether the function piecewise again f of x sin x over x if x is not equal to 0, 1 if x equal to 0, continuous at x equal to 0. Okay, now let us check the function is defined. So f of 0, what we are using it, f of 0, 1, 1, good. Second one, we are using it, right? So f of 0 is defined, the function defined, okay? Now we do check second condition, which is the limit exists. So we check x approach to 0 from the left. Okay, so picture is better. So we had a whole for the sin x over x, right? We know that. This is the third time we did that, okay? Sin x over x when x approached to 0, right? Okay, now the second function f over x equal to 1 when x equal to 0. So we're gonna have the whole like this. Okay. Now we defined the limit when x approach to 0 from the left. What do you get? Oh, you don't know this one. Okay. What do you get?
1.
1, right? How about from the right?
It would be the same thing, right?
Yeah. And remember, we did this one yesterday, right?
Was that one for the squeeze theorem? Or
Yeah, even yes. I showed you the theta approach to 0. What's the limit of sine theta over theta, right?
oh yeah, it's 1.
Oh, this one, right? Okay. Now, so limit exists. Now, third one, if limit exists, must be the same as the function f of 0, right? So there we go. Limit exists. The limit is 1. Then this is the same as f of 0. Okay, so we can say that the function f is continuous at x equal to 0 because they satisfied 3 conditions at the same time. All right?
I have a question.
Mhm.
Just, I think the only reason this is odd or confusing is because there's clearly a hole there. So
Yeah, but then the piecewise function sine x over x has a hole, right? But this one make up that hole. That's why I put the blue.
oh,
Can you see that?
1 if x equals 0. Oh, yeah.
Mhm.
I think I just wrote that down wrong. I didn't understand it was piecewise. Thank you.
All right. Good question. Okay. Now let us talk about polynomial theorem. Theorem 2.8 continuity of polynomial and rational functions. Okay. So they say the polynomials, we know that the continuous everywhere, everywhere. And rational function continuous in their domain. So we restrict the domain, the denominator cannot be equal to 0, right? Functions are continuous at every point in their domain. Means, okay? Let me erase. For what values of x is continuous here? We know that. What is that?
Everywhere except for x equals 5.
Good. So continuous everywhere. Thank you. X cannot be equal to 5. So except 5, same, right? Okay, good. All right, so let's talk about the discontinuity. Like earlier, we did that. Okay. Types of discontinuity. We had this kind of discontinuity earlier, right? Okay, so we called this is removable, removable discontinuity. So let me write down definition later. Discontinuity. Unity. Okay, so basically there's a hole. Okay, and we have this kind of discontinuity we talked earlier, right? Then we call this is jump discontinuity. Okay, then we have like there is asymptote like this. Okay, then we call this is infinite discontinuity. Okay, so basically removable discontinuity, like we had a fraction earlier, right? So when I introduced this one, we had like x squared minus 4 over x minus 2, right? Okay, so domain x cannot be equal to 2, right? But then there's no asymptote because we find the vertical asymptote in the lowest term, right? So if we simplify this one, then we get the x plus 2. So x plus 2, how do we draw? It's a straight line, right? But then there is a hole at x equal to 2 because the domain restriction, x cannot be equal to 2, right? Okay, now I'm gonna write down definition. So let me erase the bottom, the example. So that we can understand the definition with the picture together. Look. We say that discontinuous at A let me denote it this way. Continuous at A, then first one, removable. Let me just make a short. Okay. The limit exists. We know that, right? From the left, the number, right? From the right, the number. We did that earlier, right? So agree, limit exists? Yes or no? Hello, hello.
Yeah. Yes.
Yeah, right? We did it earlier, right? So this kind of a picture, graph, limit exists, right? Second one, jump, discontinuity. This is the piecewise function, right? Then piecewise, let me see. The left side, right side, the limit does not agree, right? So look, if we say the left, let's say the 1 there, okay? If we say the limit from the right, let's say the 2 there, okay? So from left, from right, it's not equal, okay? Third one, infinity, discontinuity. So basically, we take the limit, then it goes to positive infinity or negative infinity, okay? So one side limit equal to plus minus infinity, or other side goes the same thing, plus minus infinity, all right? Is it good? Okay, so let us do example. Let me erase. Okay. We showed this one is discontinuous at x equal to 2. Okay, now they say to classify this discontinuity as there's 3 types. One is removable, or jump, discontinuity, or infinity.
I'm pretty sure it's removable discontinuity.
Yeah, so this is a removable, right? Then by looking the curve graph, we can say that there is a removable, but by definition, we have to show the limit exists, right? Okay, so let's see. X approach to 2 from the left. Okay, so maybe we can say that just the 2, because we did it last time. So 2. Okay. Look, we did that indeterminated form last time, right? Then we are using the technique, factoring out, canceling out, right? Simplify. We did that last time. So we have this. We need the parentheses, maybe here. What do you get? 2 plus 2. 4. Thank you. So we say that this is discontinuity at x equal to 2, and this is a type of removable discontinuity. Discontinuity. X equal to 2. Is okay? All right. Let me erase. How about this one? We showed that. So piecewise. And 4x minus a straight line is discontinuous. X equal to 3. Classify. I have to write down again. Discontinuity as removable jump or infinity. Okay. So how did we do this one? So this one, like let me sketch it approximately like that. Remember we did that?
So it's jump discontinuity.
It's a jump. Then if this is a jump, then we're gonna show that the one side limit does not agree, right? All right, so we do limit 3 from the left and which one we're gonna use? From the left.
Negative x squared plus 4.
Good. Okay, and that is, we plug in. So what do you get?
Negative 5.
Negative 5. Three from the right, which one we're gonna use?
4x minus 8.
So what do you get?
4.
4. Okay, so they don't agree. So jump discontinuity. x equal to 3. Make sense? Okay, let us do more, huh? Let me erase. Determine whether the function x plus 2 over x plus 1 is continuous at x equal to -1. If the function is discontinuous at x equal to -1, then classify the discontinuity as one of 3 types, right? Removable, jump, or infinity. So is it continuous at x equal to -1?
No.
No, so f over -1 is undefined, right? Okay, then since this is discontinuity, continuous, at x equal to -1, we have to think about, is it removable, jump, or infinity? What do you think?
Infinity.
Infinity, right? So infinity, then we have to show that the limit approach to positive infinity or negative infinity, right? So let us do that. So one side limit. Oops. X approach to -1 from the left. Okay. So I gave you a tip last time. Okay. So last time I said that when x approach to -1 from the left, say, what is the left? Negative point, no, left.
9.
No, left. It's negative.
Negative 0.9, or no, negative 1.1 maybe.
1.1, right? Because negative, okay? So we plug in so negative 1.1 plus 2 and negative 1.1 plus 1. We don't have to calculate it. We just do sign analysis. So numerator is positive, right? Yes or no?
Yes, it's positive.
Yes. Okay, how about denominator?
It's negative.
Negative. So one negative, which is negative. Negative means behavior of asymptote is goes to negative infinity. Okay. Is okay. So this one goes to negative infinity. How about x approach to -1 from the right? Okay, then x approach -1 from the right to say what? Say ho, ho.
Now you can use the negative 0.9.
Negative 0.9. Thank you. All right. Okay. Then we can say that limit x approach to -1 from the right, -0.9 plus 2 over -0.9 plus 1, just to do sign. We don't have to calculate exactly. So numerator is positive. Also positive denominator, right? Which is positive. So in the behavior along the asymptote, positive means positive infinity, okay? So that is infinity, okay? So this is a infinite discontinuity. Let me write down here. Infinite discontinuity. All right. It's okay? All right, let me erase. Almost done. So endpoint continuous. Let me write down. Continuity. Continuity from the right and from the left. iPad is so hot. Okay. The function f is f of x is set. Let me write down. Set to be continuous from the right at a. Then the limit x approach to a from the right f of a. Okay. Then this is the first one. Second one. Let me make a detour. Then from left detour. Okay. Then left. So we're gonna make an x approach to a from the left, right? F of x equal to f of a. Okay. This is endpoint. Continuous at endpoint. All right, so let me write down this one. This means if we have f of x equal to square root of 4 minus x squared is, okay. How it looks like this one? Does anyone remember? Square root of 4 minus x squared. So y equal to square root of 4 minus x squared. Then y squared, we get rid of square root 4 minus x squared. Okay, then we have x is the other side, so we get x squared plus y squared equal to 4. What do you get this one? Hello? What do you get this one? What is this? X squared plus y squared equal to 4.
Square root of x plus y equals 2. Is that, what did you want us to do?
So what's the figure for this one? X squared plus y squared equal to 4.
Oh.
How do we draw? What's the graph?
I think. Is it a circle?
Yeah, it's a circle, isn't it? Right?
Yeah.
And radius equal to 2. Right? Then this one is what? Square root of 4 minus x squared. What is this?
Wait, square root over what?
Square root of 4 minus x squared. I'm talking about this. So what is that? Semicircle, isn't it?
Oh, okay.
Okay, minus 2, 2. Okay, we have a plus, minus. Plus is the here, upper semicircle, circle. Minus is the upper. What is called? Down? Make sense? So plus minus, right? Which is a circle, right? So we have only plus. So we have only upper. Is it clear? You guys okay? Yes or no?
So wait, sorry. It'd be plus or minus?
Okay, normally circle if we solve for y, then this will be plus minus 4 minus x squared, right?
Uh-huh.
That is the same as a circle, right?
Oh, okay. Okay.
Of y, right?
Mhm.
Because the plus sign here, minus sign right there. Make sense?
But wait, why do we only have the positive side? Do we?
Okay, this is what I'm talking about for the end point. All right, this is the example. Is it clear? So if we have square root of 4 minus x squared, the picture looks like that. Is it clear? Okay. Then let's talk about the limit. A, so we're gonna do, okay, we have to do minus 2 from the right. Minus 2 from the right. And what is the limit? Minus, where x approach the negative 2 from the right. So what do you get?
-2.
0?
0, okay. How about x approach 2, 2 from the left?
0.
Is also 0. Yeah, okay. So this is the same as f of 2 All right. You guys okay? Okay, let me do why always a short time? Let us do just composite cosine function quickly. So we don't need the theorem, just to do it. Evaluate. So how do we do pi over 2? What do you get? So x approach pi over 2. Cosine pi over 2 minus pi over 2, we can just do it.
1.
So cosine 0, which is 1. Good.
Yeah.
All right. All right. So let us do intermediate value theorem. So this one does not have homework, but also I have to cover it, even though there is no homework. Intermediate value theorem. Then we are done. Okay. So let me write down the theorem. F will be continuous over a closed bounded. Okay, let me talk about the bounded later. Interval AB. So bracket means closed, right? If Z is any real number between f of A and f of B, this is a condition, then there is a number C in the interval, closed interval, A and B, satisfying f of C equal to Z. Okay, so let me draw this one. So I just follow your book. Okay. Let's say that this is, here is A, this is B. Okay. We cut it off here. Then it's a closed interval, right? Then bounded means we call this the upper bound. And we call this is a lower bound. Yeah. Upper circle, lower circle. Something. Then they say that if Z is any real number between f of A and B, right? So this is f of A, this is f of B. Now Z is between there. So between here, Z, okay? Then there exists C in between A and B. So let us write down probably here. Okay, C, all right? So f of C equal to Z. That is the f of C. Okay, so we call this is the indeterminated theorem. So let us do one problem. Okay, then we are done. So sorry all the time. Okay. So let me do this one here. Show that f of x equal to x minus x has at least one zero. Okay, so at least 1 0 means there is a solution. At least one solution. So at least one solution means it must be like touched x-axis. This is the solution, okay? So I don't know how look like this function. So I wanted to show the decimals earlier, but maybe you should use decimals and then find out how it looks like, okay? So this one probably looks like this. All right, so how do we show this one? We're gonna show the opposite sign, okay? So at least one solution means, so between here and there, we cut it off the closed interval, okay? Then opposite sign means below x-axis, above x-axis, okay? So we can pick anything. Normally they're gonna give us the interval, but in this case they don't give us. So let me just follow the book since we don't have time. So let us using show opposite sign. So we know that this is continuous, okay? F of 0, so 0 minus cosine 0, what do you get? Cosine 0?
I think cosine 0 is 1, so would it be negative 1?
So it's a -1. So -1 is less than 0, right? And we have to show that this is the other one is greater than 0. That is the opposite sign. One is negative, one is positive, right? So what do you get? This one, cosine pi over 2. Cosine pi over 2. Cosine pi over 2, what do you get? 0. So we have a pi over 2. Pi over 2 is the positive number, so it's greater than 0, okay? So this is the opposite sign. So one is below x-axis, one is above x-axis. So we can just say that by intermediate value theorem. So let me denote IVT, that means intermediate value theorem. So we can say that there exists C is in 0 and pi over 2. Okay, we just set it up. That satisfied f of c equal to 0. This is the solution, right? Okay, so therefore f has at least, it might be more. Okay. So any question about, okay, hold on 1 second, let me erase this one. And let me turn off.